Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so we're thrilled to have Eric Maskin here from the IAS. He was in Cambridge for a long time, but I guess you moved to Princeton, what?
9 years ago.
9 years ago, okay. So he's been in Princeton for a long time, too. He's, of course, a great economist who's won all kinds of awards. I can't remember any, but he's won all kinds of awards. Okay, and he will talk about elections and strategic voting, Condorcet and Borda.
Thank you. Thank you. Please do feel free to ask questions or make comments at any time. I know this is a diverse audience, and many of you may not have seen any voting theory before, and that's okay. I will try to make this as self-contained a talk as I can, but if I mess up, you should ask for clarification. This is joint work with my old friend Partha Dasgupta, who's at Cambridge University. And we're interested in studying voting rules, which are an example of social choice functions. A social choice function is simply a rule or a method for making collective decisions, choosing a social alternative, a candidate in the case of an election, on the basis of citizens' preferences. In the case of an election, this would be voters' preferences. And we're all familiar with a large variety of voting rules from practical experience, but also from theory. Let me mention a few of the best-known voting rules. First of all, there's plurality rule, which is also called first past the post in Britain. It's the rule under which we elect members of Congress in this country, and they elect MPs in that country. And basically, it consists of each voter voting for a single candidate, a single alternative, and the alternative that wins, the candidate who wins, is the one who is voted for more often than any other, even if that candidate does not get a majority. So that's plurality rule, and it's often contrasted with majority rule, or Condorcet's method. Under Condorcet's method, we look for the candidate or the alternative who would beat each other candidate in pairwise comparisons. So the winner under Condorcet is the candidate who gets a majority over every other candidate. Now, there may not be such a candidate, and I'll come to that problem later, but if there is such a candidate, we say that he or she is the majority winner, or the Condorcet winner. Then there's runoff voting, and there are various versions of this, but probably the best known version is the one that's used in presidential elections in France. And there, once again, voters each vote for one candidate, And if there's a candidate who gets a majority of votes after that round, then that candidate is elected. But what normally happens is that no candidate gets a majority, in which case the top two vote getters go on to the runoff round, the second round, and whichever of them gets a majority in that second round is elected. So that's runoff voting, also quite widely used around the world. Then there is rank order voting, which is sometimes called the Borda count. Condorcet and Borda were both, they were almost exact contemporaries. They were both members of the French Academy of Sciences in the late 18th century. They turned into more or less arch enemies because they each had their own favorite voting method. Condorcet, the majority rule, which I already described, and Borda, rank order voting, which probably is familiar to many of you because it's used a lot in committees for, say, electing a chairman. And the way that it works is that each voter ranks all the candidates from best to worst, and a candidate gets 1 point every time some voter puts him first, 2 points every time he's ranked second by some voter, and so on. And then we just add up all the points that candidate gets, and the winner is the candidate who has the lowest point total, because a low number of points corresponds to a high ranking. So probably many of you have used this in some committee or other that you were on. And that brings me to the final. Well, I'll probably talk about other voting rules later on, but the final one I want to mention now is the utilitarian principle. The utilitarian principle, which is dear to economists in particular, because economists are obsessed with maximizing utilities. Under the utilitarian principle, voters in effect submit their utility functions, and then we look for the candidates that would maximize the sum of utilities.
So the others could be special cases of that sometimes or not? With a properly chosen utility function.
Well, the others are related to this, but they're not actual. They're not. None of them are exact special cases, except, well, I suppose you could say that rank order voting is a special case if you insist that the utilities be equally spaced. That's right. Right. So in that.
But in general, the other ones all use ordinal information, whereas this one does require some kind of cardinal.
I see.
Information.
And you're
That's
getting
right.
the cardinal out, or the ordinal out by requiring the equal spacing, right, to get the
So
cardinal.
that would
Rank order voting, that's right. Rank order voting becomes ordinal because you're taking whatever cardinal information you might have had away by insisting on the equal spacing. So 1 point to 2 points, 2 points to 3 points. I'll come back to the difference between cardinal rules and ordinal rules later on. In fact, cardinal rules are rather problematic, particularly in one-shot elections. In sequences of elections, for reasons that I will come to, it might be possible to introduce some cardinality, but in one-shot elections, they are certainly problematic, and that will be one of the themes, one of the main themes of the later discussion. Anyway, I just talked about 5 different voting rules that could be used, and some of them often are used. Most of them are often used in practice. But with such a multiplicity of voting rules, and there are many others that I could have discussed, we're confronted with the question, well, which one should we actually use? And of course, the answer to that question will depend on what it is that you actually want out of a voting rule. And the way that voting theory normally proceeds is to start with the basics. That is, what you first need to do if you're trying to decide which voting rule should we have is to decide what are the criteria, what are the axioms or the criteria or the objectives that we are trying to satisfy. And that's normally how voting theory proceeds, axiomatically. That is, we specify the axioms, and then we see which voting rule comes closest to satisfying those axioms. Well, one important criterion, and that's the one that gives this talk its name, strategic voting, is the idea that elections should not be subject to a lot of strategizing. One way of putting that is to say that they shouldn't be manipulable by strategically minded voters. There are lots of reasons why we might be concerned about manipulation. Let me just mention 2 of them. First of all, if voters are voting strategically, that means in effect they're voting not according to their true preferences, but to according to some manipulated preferences. In effect, we're not implementing the voting rule that we thought we were implementing, because the inputs are different from the inputs we were expecting. And if the inputs are different, then the output will be different. The elected candidate will be different. So if, according to our other axioms, we thought we had a good voting rule, but that voting rule turned out to be manipulable, then in effect the other axioms might go by the wayside too, because we're in effect implementing some other voting rule altogether. So that's one reason why manipulability is possibly a matter for concern, but I think an even more basic reason is that when voting rules are manipulable, it makes it harder for voters. Even figuring out your own preferences in an election is a non-trivial matter. If you're going to try to compare candidate X with candidate Y, well, typically that involves a significant investment in finding out what those candidates are proposing to do. But if on top of that you have to anticipate what other voters' preferences are, then the problem is an order of magnitude even more complicated, because for me to figure out how I should vote if the voting rule is strategically manipulable, I have to anticipate how you're going to vote so that I can respond to that. And that is a lot harder. And elections are hard enough for voters without introducing that additional complication. So simply to keep decision problems as simple as possible, it's probably a good idea to try to reduce manipulability. Unfortunately, there is a well-known negative result about non-manipulable voting rules. It's called the Gibbard-Satterthwaite theorem because Alan Gibbard and Mark Satterthwaite discovered this more or less simultaneously. And what it says is that if there are 3 or more candidates on the ballot, then there is no voting rule, or no, strictly speaking, we have to qualify that a little bit. But basically, there's no voting rule that we would ever want to use that is always non-manipulable. The only voting rules which are invulnerable to manipulability are what are called dictatorial rules, rules where one voter has all the power. But clearly, voting rules like that are not very attractive from a democratic standpoint, so we tend to rule those out. Well, this negative result sounds quite discouraging, but there's a sense in which it's misleading in its pessimism. I would argue that it's more pessimistic than it should be, because what the Gibbard-Satterthwaite theorem shows is that any voting rule, or any non-dictatorial voting rule, is sometimes manipulable. But it could well be the case that the circumstances under which it's manipulable are not very likely, in which case we might not worry very much about this manipulability. So from our standpoint, the natural follow-up question to this negative result of Gibbard and Satterthwaite is, well, which voting rules are non-manipulable as much as possible? We can't get rid of manipulability altogether, but we can try to reduce it to a minimum, make it as unlikely as we can. And that's the subject of this paper. We have a particular way of trying to answer that question. Yeah.
If you only have 2 candidates, then all of the voting rules are not.
Basically, if there are only 2 candidates, almost all voting rules that we would ever use in practice are equivalent. That's not actually quite true. The utilitarian, of the ones I mentioned at the beginning, utilitarianism is a bit different. But the other 4 are all non-manipulable, and they are all equivalent to just taking a majority vote between the 2 candidates. Under utilitarianism, you might get something else, but under the other 4, you would always get the majority winner. So the 2-candidate case, although it often happens in practice, is actually not very interesting from a voting theory point of view. It's too easy. Susan, hi.
This would be an interesting place to give a little perspective
Mhm.
about the times when economists are more and less attached to sort of using a Bayesian perspective versus trying to get things that are sort of never manipulable. In a sense that
Right.
a lot of
Yeah.
Deborah's laughing because we have these arguments.
Yep.
A lot of the science talks are very attached. They sort of stop here and not be happy about the step you're about to take.
Well,
While in some sense, a lot of like auction theory.
Well, actually, as it will turn out,
Are very happy.
I'm not going to take a Bayesian point of view here. So in a sense, I think it will turn out that without calculating, without making use of probabilities at all, I am going to answer the question which voting rule is least manipulable.
I guess it would be interesting though to think about. So why have economists been happy to take a Bayesian perspective in some problems like auctions, and yet here you're working very hard still to not do that?
Yeah.
And so that perspective.
That's right.
Hard when economists do it one way versus another.
Yeah. Well, I think one reason why we wanted to avoid probabilities in this problem, although I should say that there is a significant voting literature that does take a Bayesian perspective, it is that we wanted results that made no a priori assumptions about what voters' preferences are. There are specific applications of voting theory, just as there are specific applications of auction theory, where we have a reasonable idea of what the class of preferences that are likely to arise might be. We wanted this theory to be more generally encompassing than just to those applications.
This problem is that if in voting context, with multiple provincial choices, we naturally think of the preferences as being ordinal. And so there's sort of a really big leap to take those preferences from being ordinal to cardinal. While in auction theory, we're sort of happier to think about somebody maximizing profits and comparing dollars to dollars.
You can still build up priors of
Well,
cardinal risk. And you have a lot of polling information and stuff, so you can't claim that these types of scenarios don't have ordinal, don't have Bayesian information.
the argument against cardinality isn't so much, well, I was going to get to that later, but why don't I bring it up now? The advantage that an auction has compared with an election is that in an auction you can always evaluate the intensity of preference by how much money the buyer is willing to pay. In an election, how can you, if you like candidate X more than candidate Y, and this is a one-shot election, there is no operational way that you can say, that you can express that how much more you prefer X to Y. In order to be able to express intensities, you have to trade off the choice between X and Y against something else. And normally in elections, we don't give people that opportunity. We don't, or at least we try to avoid giving them the opportunity to buy, for us to buy their votes. Now, there have been some creative and interesting proposals for introducing cardinality into elections by allowing people to accumulate votes over a sequence of elections. So say I didn't care much about the issues in election A, but I cared a lot about what was going on in election B. Well, I might decline to vote in election A in exchange for getting 2 votes in election B. That's a way by which I could express a cardinal preference. But in a one-shot election, which is the norm in elections, where we don't link issues up intertemporally, there is just no effective way that I can express an intensity. And that, I think, is an important difference between auctions and elections.
So you're saying to use Bayesian analysis, being able to express intensities is the crucial?
No, I was even with ordinal preferences, we could still talk about the probability that we have this ranking rather than this ranking. However, we don't typically have very good information about what those probabilities are. Now, the people in election theory, in voting theory, who proceed in a Bayesian fashion, what they typically do is to assume that all rankings are equally likely, and you can make some headway assuming that all rankings are equally likely. If it had turned out that was the only way we could get our result, then possibly we would have settled for that. I would have personally felt pretty uncomfortable about that.
I'm not sure if people warned you. I mean, I did warn you that we're a very, very inquisitive,
That's great.
talkative
No.
audience, and the seminar will go on until you're finished, at least 5:30, but it'll go on until you're finished since we're constantly.
No,
But Silvio has to say something on that note. Silvio.
Yeah.
To the naked eye, not to use the Bayesian is a big plus. I mean, I cannot make fun of it.
To the naked computer science eye.
Well,
Bayesian essentially is assume that you have some.
That you know the distribution.
yeah. Well, that's right. And as you will see.
Most mean without I mean,
Well,
that's the part that's been confusing
Right.
me. You said no.
You will see.
So I want to let him go on.
You will see.
What's most mean?
There is a well-defined sense.
So that's the interesting.
But I am glad to discuss these conceptual issues like the one that Susan raised, because they're important. So don't worry about raising them.
I wouldn't know how to change a sentence.
Okay. So let me first set up the model that we use, and then I will show you what results we have from the model. So in most respects, for those of you who might have seen some voting theory, in most respects there's one departure from the standard framework, but in all other respects this is a very standard voting theory framework. There's a finite set of social alternatives. So there's a finite universe of possible of candidates who could conceivably run for office, and by contrast, we'll suppose that the set of voters is infinite, it's a continuum, and this is the departure from the usual assumption, and it's made basically for a technical reason that I'll explain in a minute. This is the only non-standard feature. So there's a continuum of voters, and a voter can be described by his or her utility function, which assigns a utility to each candidate. And I'm, again, going to make a technical assumption. I'm going to assume that utility functions are strict, which means that I'm ruling out indifference. That is, two candidates cannot be assigned the same utility. It turns out that things are a lot messier without being correspondingly clearer if we do allow for indifference, so I'm simply going to rule it out. And now we can describe a society by describing the utility functions of all the people in that society. And so U sub box will be what's called a profile. Profile is a specification of everybody's utility functions. And when we replace the box by I, then we're looking at voter I's utility function. So a voting rule takes these profiles and takes the set of candidates who are actually running for office, which will be a subset of all of the candidates who could run for office. So given the profile U box and given the subset of candidates who are actually running Y, well, I'll refer to this as the ballots, the voting rule chooses a winner, selects a winner from Y. So you can interpret this as the winning candidate or the optimal alternative or the compromise alternative, whatever interpretation you want. But actually this definition isn't quite right because it rules out the possibility of ties. And in fact, all of the voting rules that I was telling you about at the beginning could allow for ties. We could have an exact tie with plurality rule. We could have an exact tie with majority rule, with all the voting rules I was talking about. However, if there are a lot of voters, the chance of an exact tie is very unlikely. And that is the reason for assuming a continuum. It's the only reason for assuming a continuum, just to make exact ties unlikely. So the correct definition is that we want the voting rule to choose a winner for a generic profile, or put another way, for almost all profiles. Okay, so that's the model, and now we can formally define all of the voting rules that I was talking about before. So this is how plurality rule will look. We choose as the winner the alternative A that is put first by more voters than any other alternative. So let me explain that here. So mu here is, we have a continuum of voters, so we have to have some way of measuring the size of a voting block, and mu is the way that we do this. Formally speaking, it's Lebesgue measure. If you don't know what Lebesgue measure is, it's just looking at the proportion of people in the unit interval from 0 to 1 who have a particular preference. So we're looking at the proportion of people who put A above all other alternatives B, and the plurality winner will be the alternative A that is put first by a higher proportion of voters than any other alternative A prime. So that's plurality rule. And similarly, we could define majority rule and rank order voting and utilitarian principle and so on, but I'm not going to go through those. But now we come to the crux of the matter. I said that the way that voting theorists proceed is axiomatically, so we have to say what it is that we want out of these voting rules. And here I'm going to look at absolutely standard axioms, that is, axioms which have a very long history. One of them will be controversial, or has a controversial history, although as I will argue, it also has a strong justification. But the others, I think, are quite uncontroversial. And one of the axioms is non-manipulability, but I'll save that one for last. I'll look at the other properties which are even better known first. The first is what's called the Pareto property, or you might call this the consensus property. It just says that if everybody agrees that candidate X is better than candidate Y, if everyone likes X more than Y, and furthermore, if candidate X is actually on the ballot, then we shouldn't elect Y. It would be pretty perverse if we elected Y if everybody prefers X. So that's not very controversial.
People from Iran are smiling.
I'm not saying 99%. I'm 100% prefer X to Y, even in Iran. Anonymity, also very standard. Basically, anonymity says that every voter should count as much as every other voter. And the formal way that we express this is to say, start with a particular profile, and now permute the profile so that person I gets J's preferences and J gets K's preferences and so on. Mix everything up, but keep the distribution of preferences the same as before. Just the identity of the people who have those preferences is changed. Well, if we elected X before, we should still elect X. It shouldn't matter who the voters are. It should just matter what their preferences are, and that's what anonymity says. Now, because we're working with a continuum, it turns out that when we do the permutation, we have to make sure that we don't change the size of the group when we make the permutation. There's some technical issues to worry about, but I'm not going to go into those. That's anonymity. Then the next property or axiom says that just as we want to treat all voters equally, we also want to treat all candidates equally. Neutrality insists on that. And what neutrality says is, suppose that we change the names of the candidates. So candidate I is given J's name, and candidate J is given K's name, and so on. If we permute the names of the candidates, then we should also permute the outcome of the election in exactly the same way. So that's what neutrality says. And you won't be surprised to learn, and perhaps you knew this already, but basically all the voting rules that I've talked about, plus many, many others, satisfy all three of the properties that I've defined so far: Pareto, anonymity, and neutrality. It's the next axiom which starts to differentiate one voting rule from another. And that's one reason why it's been certainly the most controversial axiom. But as I said, it does have a, I would argue, very persuasive justification. That's why it was put forward in the first place. And it also has a very good pedigree, because it was proposed more or less at the same time for somewhat different reasons by Kenneth Arrow in his work on voting theory, and also by John Nash in his work on bargaining theory. Their formulations are a bit different, but they're getting at very similar ideas. I'm actually going to use the Nash formulation today. And this axiom goes under the name independence of irrelevant alternatives, or since we're talking about elections, we could call it independence of irrelevant candidates. And it says this: suppose that for a particular profile and ballot we elect candidate X, and now some of the members of that ballot, some of the candidates on that ballot drop out, but X does not drop out. Well, in a sense, the other candidates, the ones who dropped out, were irrelevant because they didn't get elected anyway. So it shouldn't make any difference that they dropped out, should it? Well, independence says that it shouldn't matter. X should still be elected if these irrelevant candidates drop out. And that's the essence of the independence requirement. Now, why has it been? Why did Arrow in particular make such a big deal about independence? Why is it so important? It's important because there have been many famous elections in practice where, because of a violation of independence, many people would argue the wrong candidate got elected. And let me just give you a couple of recent examples. Yeah.
You are arguing in favor, right?
Yes.
So, but assume that there is an election and Bush wins.
Yeah.
The latest Bush, not the senior.
Yeah.
But then
I was going to use that election actually, but.
But assume that there are also Hitler and Stalin.
Yeah.
Already. And someone between Hitler and Stalin and Bush say, hey, you know what, I vote Bush. But if all of a sudden Hitler and Stalin drop out, then it isn't so clear to me that I would vote for Bush. Or I would
Well, if Bush is the only one left, according to the example you're giving. Depends who else is.
But so you're saying that then I don't understand what is written there. So I may
All right.
He's saying you can't be strategic in that way.
So that means
No.
that they
I'm saying that. Let me talk about the example that I was going to concentrate on the next slide, which is, let me talk about it right now. It's the 2000 U.S. presidential election. There were essentially three candidates that people discussed. There was Bush, there was Gore, and there was Ralph Nader. And you probably remember that everything came down to the state of Florida, where Bush very narrowly got more votes than Gore. Out of about 5 million votes cast, Bush got 500 plus more votes than Gore did. But Ralph Nader was also on the ballot, and Nader got almost 100,000 votes in Florida. If Nader had not been on the ballot, there is very good evidence of a variety of forms which suggest that most of the people who did vote for Nader would have voted for Gore if they had voted for all. Some of them might not have voted at all, but of those who actually did vote and would have voted, and the majority would have, at least according to the evidence that we have, overwhelmingly those voters would have voted for Gore, in which case Gore would not only have won in Florida, but he would have won quite comfortably by several tens of thousands of votes, not by a razor-thin majority. So Nader was an irrelevant candidate in the sense that he had no chance of winning. No one ever thought Nader had a chance of winning the election. But he changed the outcome of the election from Bush to Gore. And this is by no means the only example. It may be the most infamous example in living memory, but there were loads of elections in U.S. presidential history and loads of elections in European political history which had similar features. The French election of 2002, I was talking about this with Daron earlier, was similar. Some of you may remember that in that election there were, again, 3 candidates of note. There was Jacques Chirac, who was the incumbent. There was Lionel Jospin, who was the primary challenger from the left. And then there was an extreme right-wing candidate named Le Pen, Jean-Marie Le Pen. And I mentioned that France has this runoff system. Everyone expected going into the election that it would be Jospin and Chirac in the runoff. And some polls favored Chirac, some polls favored Jospin. Actually, probably most of them favored Jospin. So he was somewhat favored going into that election. But then it turned out that that after the first ballot was taken, Chirac got the most votes and Le Pen got the second most votes. And the reason Le Pen got the second most votes was because the vote for left-wing candidates was badly split. So Le Pen snuck into the runoff because of this badly split left. But by so doing, he could well have changed the outcome of the election, because if it had been Jospin against Chirac, which was what everyone was expecting, Jospin could very well have won. It turned out that Chirac won.
But if this assumption is true, then it doesn't make sense to have 2-round elections.
Well, 2-round elections will violate this assumption, sure.
But if in their example of Bush and Al Gore, if there was a second round of election, that wouldn't happen after Nader dropped out, right?
In that, yes. If the United States had used runoff voting, as France does, then Al Gore probably would have been elected. But that doesn't mean that runoff voting satisfies independence, because although in that particular example it did, in the French example it didn't. So both runoff voting and plurality rule violate this assumption. Yeah. No. Runoff voting is not okay if you have three alternatives. The Chirac, Jospin, Le Pen example was only three alternatives, and it violated runoff.
The left vote was split between Chirac and...
Oh, I see. No, you're right. The way I described it, it would have been okay. But let's, I don't know if I should use the board or not. Well, I can just talk you through. Even with three alternatives, it's quite possible for the majority winner, say Jospin, to be the to have the lowest vote total among first place votes. Let me see if I can construct a quick example. Suppose we had 35% putting Chirac, Jospin, Le Pen, and 4% Le Pen, Jospin, Chirac, and what's the remaining 31%? Jospin, Chirac, Le Pen. Then Jospin is the majority winner. Jospin beats Le Pen by an overwhelming majority. These people and these people, that is 66% prefers Jospin to Le Pen, and Jospin also beats Chirac by an overwhelming majority. These people prefer Jospin to Chirac, and these do. That's 65%. But Jospin comes lowest in the first round because he'll get only 31% of the vote. So even with three candidates.
Preferences aren't like single peaks.
No, they're certainly not single peaked, but single peak. Well, I'll come to single peakness later. There are situations where single peakness may be the guiding force. There are situations, and I think France may have been one of them in this election, where there are other considerations.
So by this independence of the relevant alternatives, basically what you want to do is to have an election in which even if Nader did not run for office, Bush was elected again, right?
Yeah, or put another way.
Reality, the theory, rather than
That's what it says. That's what it wants, right?
Sure.
Or that Gore would want to see
Right.
In the first place.
You just want the same. You want the same. You want the same outcome, whether or not Nader is on the ballot, and the reason for that is that someone like Nader or someone like Le Pen, fairly marginal figure, should not have the power to utterly transform the outcome of the election. That seems quite undemocratic, and yet it's happened many times in reality.
The one that all known electoral schemes are missing, and isn't that the reason? I mean, if you gave me an electoral voting scheme which had satisfied this axiom,
Yeah.
shouldn't we be done? Shouldn't that?
Well, okay, so So there is something called the arrow impossibility theorem, which says that the axioms that I already showed you plus this cannot simultaneously be satisfied. And that's why we have to ask a follow-up question. Well, sure, we can't satisfy all of these axioms all the time, but maybe we can look for a voting rule which satisfies these axioms more often than any other. And that's the guiding spirit behind our research program, to try to satisfy these axioms as often as we can.
But this alone can be satisfied? This alone can be satisfied?
Well, for example, a dictatorship will satisfy this principle. If there's only one voter who matters, then we'll satisfy. It was ruled out by the other axioms. It's ruled out in particular by anonymity. Anonymity says that all voters should count equally. That's at odds with a dictatorship.
Doesn't Condorcet satisfy this?
It does, but there are times when there's no Condorcet winner.
That wasn't an axiom. That wasn't an axiom.
Yes, when I defined a voting rule, I said that there should always be a winner. And Condorcet doesn't always produce a winner. So Condorcet has to be completed somehow. You have to say what happens if there is no Condorcet winner. And then we run into problems satisfying this. Okay, so,
Take another question,
oh yeah, sure, as many as you like.
So I've heard the independence of irrelevant alternatives applied to ranking systems where a ballot ranks all the candidates, in which case it's sort of meaningful to say that something is irrelevant because you remove those and you still have ranked the others.
Mm-hmm.
In the case where it's a plurality system and you remove the one candidate that I voted for, then I lost my entire vote. And in fact, in the Florida case, if you removed all the votes for Nader, then the result would be the same as we got.
Oh, but what you would do if the thought experiment is what would have happened if Nader had decided, I don't know how long you have to decide whether you're going to run or not. If at the last minute Nader had dropped out, so people would have had an opportunity to vote for someone else, even if they had been planning to vote for Nader. Would the fact that Nader had dropped out have made a difference? And Independent says it shouldn't make a difference because Nader wasn't going to win in Florida anyway.
I guess since people weren't given an opportunity to rank people on their vote,
Yeah.
then it's not meaningful to talk about what would have happened because we don't.
Well, we don't know what would have happened. Yes, I said that
The voting system didn't capture it.
the voting system itself didn't capture, but that you can say is another drawback to plurality rule, the fact that we're not getting enough information about what voters actually want into the formal system. We can get some of this information indirectly through exit polls and through surveys and the other forms of extra electoral information that we have, but you're right that it's not actually being, this information is not being captured by the voting rule itself, and that I think is a problem with the voting rule.
Okay, we're going to let Eric.
Okay. Okay. So majority rule and utilitarianism satisfy independence. Majority rule with the qualification that majority rule doesn't always produce a winner, but when it does produce a winner, it does satisfy independence, almost by definition, because because majority rule always looks at pairwise comparisons. If some third candidate drops out, the pairwise comparison between the two remaining candidates is still the same, and so we get the same outcome between those two candidates. Utilitarianism also clearly satisfies independence, but plurality rule violates it. Well, I already talked about that, and rank order voting also violates independence. In fact, this is one of the major arguments that has been used against rank order voting, the fact that it violates independence in a very extreme way. Rank order voting is highly vulnerable to violations of independence. And here's a simple example where there are 3 candidates, X, Y, and Z. A majority, 55%, prefer X to Y to Z. The rest of the population prefers Y to Z to X. According to rank order voting, candidate Y is the winner. Y is in the minority, but Y happens to be ranked second by the majority group, and whereas candidate X is all the way at the bottom for the minority group. So that's enough to make the difference when you're counting up points to get Y elected. But if Z drops out, Z is the irrelevant candidate here, so he has no chance of winning. If Z drops out, then X gets elected because now we have just a straight majority comparison of X and Y. So rank order voting very visibly violates independence. Okay, now we come to the final axiom, which is actually the one that I started with, non-manipulability. And here's what it says. Suppose that we have 2 profiles, U box and U prime box. And suppose that these 2 profiles are exactly the same except for this coalition of voters, this subset of voters, C. Then it should not be the case that this coalition of voters should all gain by announcing preferences U prime rather than U unprime. So in other words, there should be at least one member of the coalition who does not gain by distorting his preferences from UI to UI prime.
You're assuming some kind of strict, you're assuming that all the rankings...
Yes, I ruled out indifference, and this is one of the places where ruling out indifference really helps.
And the other people in the coalition could lose?
Sorry?
What about the other I and C?
Well, it doesn't, as long as there's one person who does not gain from misrepresenting, then we say that this is non-manipulable, because it just takes one person to say, I'm not going along with this distortion. So that's non-manipulability. Sorry?
What is C? Is there like a quantification?
C is just some subset. Yeah, I'm sorry. This has to be true for all C. Yes, I didn't quantify it. You're right. Yeah. Yeah. This is for all C and for all X and for all X prime and for all profiles U box and U box prime, which satisfy this. Right.
So here it's crucial that these other guys cannot compensate J, right?
Yeah, that's right. For this kind of misrepresentation, you have to gain yourself. You can't be bought off by someone else. That's right. And we could certainly modify the definition to take into account compensation if it were available, but it's not available, so we don't.
You have your coalitions theory, but you could do it one person at a time.
Yes, actually, it turns out to be the same, and that's another benefit of working with strict preferences. It turns out that coalitional misrepresentation is, well, let me back up. I'm working with a continuum of voters here, so we can't really do it one person at a time because one person doesn't make any difference. But if there were a large but finite number of voters, then coalitional misrepresentation and individual misrepresentation would amount to the same thing as long as there are strict preferences. Yeah.
One thing that comes a little surprising to me is that because before you had a continuum, you care about things not to be, you wanted a continuum for having things which are not very rare to happen. And all of a sudden, when you quantify for whole C, you don't care if it is measured 0 or not. The C is just a bit disconcerting. Maybe I should not worry about it, but.
Well, yeah. You're saying that this is a demand. This is a demanding condition. Yeah.
But you can satisfy.
But it looks superficially it looks demanding, but it turns out that it wouldn't be any different if we demanded that this hold for some group of voters with positive measure. It would be exactly the same. Yeah. So it's superficially more demanding than it actually is. Okay, so I discussed the idea of ordinality versus cardinality earlier in the interchange with Susan, and the big problem that cardinal voting rules run into is that they're always going to be manipulable. Now, what do I mean by a voting rule being ordinal? I mean that if we have two profiles which give rise to the same rankings, they might give different utility numbers to the alternatives, but the ordinal rankings are the same, then the winners are the same. And it's very easy to show that any voting rule which is non-manipulable and satisfies independence is going to have to be ordinal. Basically because if it violated ordinality, that is, if we had two profiles which were ordinally equivalent, which gave rise to different outcomes, then the people who preferred X to Y would always gain by misrepresenting their preferences so that we got this outcome, and the people who preferred Y to X would always gain by misrepresenting their preferences so that we got this outcome.
So you've got coalitions there that can manipulate.
Right. So cardinality is a non-starter if we require non-manipulability. And that's a major reason why so much of the voting literature has concentrated on ordinal rules. Now, unfortunately, majority rule, which was the only rule left. We got rid of utilitarianism because that's cardinal because of non-manipulability. Unfortunately, majority rule also violates non-manipulability, and that's because majority rule doesn't always produce a winner. It's not always well defined, and probably most of you have seen this famous example. It's actually called the Condorcet paradox, because Condorcet was the one who, to the best of our knowledge, first pointed it out. Is there anyone who hasn't seen this example of intransitive? Fine.
And that probably means that he's the only one who admits that he hasn't.
Okay. So I said that the Condorcet winner is the candidate who would beat each other candidate by a majority. But there may not be such a candidate, and here's an example. X can't be the majority winner.
Well, yeah, but
Okay.
he just saw it a few minutes ago, but he didn't know the name.
Well, actually, that's not a Condorcet. This is a Condorcet cycle. In this example, X cannot be the winner because a majority of people prefer Z to X. These people prefer Z to X, and these do. Z can't be a majority winner because Y beats Z. These people prefer Y to Z, and these do too. That's 68%. And Y can't be a majority winner because X beats Y. These people prefer X to Y. These people prefer X to Y. So there's no majority winner. And Condorcet, even though he was putting this method forward, knew that this was a possibility. And so he suggested what voting theorists have done ever since, which is to extend Condorcet so that it is well defined. And one way of doing that, and this is a nice reconciliation between Condorcet and Borda, is to use Condorcet when it produces a winner, and when it doesn't, to use Borda, rank order voting. In fact, this is called Black's method, and I'll come back to Black's method at the very end, which is actually coming up pretty soon because I'm running out of time. It turns out that Black's method is in some sense going to be the hero of our second result. There are two results, and I'm about to come to the first one, but the second result will feature Black's method. But it's any such extension that makes Condorcet vulnerable to manipulation. It also makes it violate independence. So here's an example.
Because the extension is to rank ordering, which you showed us back.
Yeah, and it turns out that any other method that which completed will also violate
I see. So even if
this
you
axiom.
didn't do Condorcet to Borda,
No matter what you picked, you can show that no matter what you pick, it's sometimes going to be manipulable. Yeah. So we have this negative result that there's no voting rule that satisfies all 5 of our axioms: Pareto, anonymity, neutrality, independence, non-manipulability. This is actually a version of the Gibbard-Satterthwaite theorem, which I told you about earlier. It's also very closely related to the arrow impossibility theorem. But as I suggested, there's a sense in which it's too pessimistic because we're insisting that the axioms always be satisfied, and yet in actual applications, some of these rankings, some of these voters' preferences may actually be very unlikely. And
unlikely with respect to uniform measurement?
No, well, it depends on the application. So majority rule, for example, will satisfy all 5 properties, provided that we can rule out these Condorcet cycles. And Condorcet cycles are a problem, as we saw. It turns out that they're the only problem that can go wrong with majority rule. That is, if we know that there are no Condorcet cycles, or at least the Condorcet cycles are extremely unlikely, then we know that majority rule, the Condorcet method, will satisfy all 5 axioms. Now, when can we rule out Condorcet cycles? Well, one case, and someone mentioned single peak preferences before, is where there's a strong likelihood that most voters have single peak preferences. When are preferences single peaked? They're single peaked when voters vote according to their ideological perspective. So in the 2000 U.S. election, there were these 3 voters, 3 candidates, Nader, Gore, Bush. Nader was, you could think of as the left-wing candidate. Bush was the right-wing candidate. Gore was somewhere in between, probably more left than right, but in between. It's, again, going on the basis of the evidence that we have of various forms, there are probably not, there don't seem to have been many people who had the ranking Bush, Nader, Gore. Or for that matter, Nader, Bush, Gore. And another way of putting that is to say that people's preferences for these 3 candidates were, by and large, single peaked. If you graphed their ideological position versus the utility that a voter would give to these candidates, the graph of that curve, of that function, would have a single peaked, whereas these preferences give rise to a U-shaped curve.
But you're assuming that we are, and I will admit to this, very ideological, that there are not, that we can't be kind of fiscally conservative and socially liberal and have all these dimensions along which, that we tend to order ourselves in along some ideological spectrum.
Yeah, but I'm not going to insist that voters be ideological. I'm saying that this is an example where majority rule will work out just fine. It's not the only example. Another example is provided by the French election of 2002. And this has nothing to do with single peakness. There were these 3 candidates that I've been talking about: Chirac, Jospin, Le Pen. Chirac and Jospin were the sort of middle-of-the-road candidates. Chirac was somewhat to the right, Jospin somewhat to the left. Neither one of them excited a great deal of passion one way or the other from voters, but Le Pen was a lightning rod. People felt very strongly about him. A lot of people hated him. A strong but significant, a minority, but still a significant minority of people loved him. In other words, they had strong feelings. Well, it turns out that if for every 3 candidates, there's always one candidate whom voters feel strongly about, that is, they put him first or last, but never second, that's also going to rule out Condorcet cycles. So that's fine too.
This is in the case of 3 candidates.
Yeah. So
claim that a strongly felt candidate would not have Condorcet cycles.
Right. So more generally, if there are more than 3 candidates, you want there to be a strongly felt candidate among every subset of 3. That would be the more general condition. And that will also make majority rule work well. So let me define a voting rule to work well if for some set of preferences, not we're not going to include all preferences. We're going to limit them somehow, perhaps because voters have strongly felt preferences or because voters have single peak preference, some restriction. We'll say that a voting rule works well on a restricted domain of preferences if it satisfies all 5 of our conditions on that domain. So, for example, Condorcet works well in this sense when preferences are single-peaked or when preferences are strongly felt. So here's the first result. And this is the sense in which Condorcet satisfies our 5 conditions more often than any other. Take any voting rule, F, and suppose that it works well on a particular domain of preferences. Then Condorcet must also work well on that domain. And conversely, suppose that Condorcet works well on a particular domain, and suppose that on that domain, Condorcet and the other voting rule differ. They aren't always the same. Then there must exist some third domain where Condorcet works well and the other voting rule does not. So there's a uniform sense or pointwise sense in which Condorcet beats every other voting rule. If the other voting rule works well, Condorcet does too. And furthermore, if the other voting rule is not itself Condorcet, there will be cases where Condorcet works well and the other voting rule doesn't. And that's why we don't need a Bayesian analysis. It's a pointwise comparison.
But I'm still, I think this is very useful because people do tend to be ideological or have strong opinions. There's something that orders us and therefore breaks the Condorcet cycles, which is kind of, I would imagine, what's happening in proof on some level. But I think in cases in which our preferences are more subtle, when we talk about voting, we feel very strongly. When we talk about investing in a stock or something, we have much more multi-dimensional preferences. No. And there, generically, I would imagine you are going to violate this, and you are going to have Condorcet cycles. Do you see what I'm? But I don't. I can't quantify exactly what I mean by generic at the moment. Although.
Well, the point that this theorem is making is whether or not it's the case that Condorcet cycles are likely or not. If they do occur, so that majority rule doesn't work well in this sense, then no other voting rule is going to work well either. So yes, there's a problem with majority rule, but there's also a problem.
It's a much deeper impossibility theorem because it tells you kind of how to fix it, and if you can't fix it in that way, you can't fix it in any way, basically.
Well, you can't fix it in a way. In the way that we're approaching it. See, and then we might get into a Bayesian analysis. Then, if we're in a domain where no voting rule works well, then we might start counting up. Well, this voting rule has 7 violations, and this voting rule has 13 violations. That's where the Bayesian analysis comes in handy, but at this level, we don't need it. Yeah.
When you say, like, in this domain or restricted to this domain, what you mean is that there's a common belief that everybody's preferences are drawn from this domain.
Yes.
So it's the case that it happens to be for this particular preference profile, everybody's preference is from that domain.
That's right.
This is an important distinction because otherwise I think you lose the mind.
Yes, that's right. That's right. So not only is it the case that the actual realized profile is from this domain, but voters understand even before they know what the realized profile is that we're restricted to to some common domain, yes.
One quick question about the first sentences.
Yeah.
When you say if F works well in a domain U, then Condorcet works well on U also.
Yes.
What does it mean for Condorcet to work well on U? Does that just mean that there are no Condorcet cycles?
Yes. Because that's it's only because of Condorcet cycles that Condorcet may not work well.
So this is just saying that nothing can possibly work well in a domain that has Condorcet cycles.
Right.
Okay.
Yeah.
Yeah.
And that's what I was asking.
That's right.
That was their answer. They were differently phrased.
Okay, so I think I have 30 seconds left, which
We have
well, but I am not much more than 30 seconds away, so the timing worked out well because I only have one more result. I said several times that, well, if there had been time, I would have shown you some of the proof of this, but I'm not going to do that now. But I said several times that by far the most controversial axiom, although still a very reasonable axiom, was this independence assumption. And there's a large literature criticizing it, just as there's a large literature justifying it. I think it's reasonable to see what happens when we drop it, and that's what the second result does. So unfortunately, if all we do is drop it and then insist that the voting rule satisfy the remaining four properties all the time, we get impossibility again. That's another version of Gibbard-Satterthwaite. But we can take the same approach that we've been taking and say, let's look at restrictions on preferences, and we'll say that a voting rule works nicely, as opposed to working well, on a domain if it satisfies the four remaining properties on that domain. And now we have theorem 2, which, as stated, will be for the case where there are exactly three candidates. If there are more than three candidates, then we need some more qualifications. But we get a very clean result for the case of three candidates, which is that if some voting rule works nicely on a given domain, then either Condorcet or Borda, or possibly both, but at least one of them will work nicely on that domain. Furthermore, suppose that one of the two, Condorcet or Borda, happens to work nicely on a given domain. Let's call that voting rule F star. So it's either Condorcet or Borda. If the voting rule that we started with is not F star on this domain, then we can find a domain where F star works nicely and the other voting rule doesn't. So this is exactly like theorem 1, except that now instead of there being a single voting rule, Condorcet, which dominates the others, Condorcet and Borda jointly dominate the competition, and that's where the black extension comes in, because I said that according to Black, what we should do is to use Condorcet when that gives us a winner, and when it doesn't give us a winner, to use Borda. Well, that's exactly the voting rule that will beat all of the competition according to this theorem. Now I'm not going to be able to show you the proof, but there's a very simple idea behind the proof, which is this. Condorcet, as we've said, works nicely, works well, and also works nicely as long as we can rule out Condorcet cycles. It turns out that Borda works nicely precisely when there are Condorcet cycles, or when we have a domain that is a subset of a Condorcet cycle. So the two of them together are nicely complementary. They cover all the territory if we can combine them the way that the black method does. So we thought that this result has a nice historical aspect to it. As I said, Condorcet and Borda were arch enemies. They each had their favorite voting rule. These voting rules also happen to be probably the most intensely studied voting rules. They go back 200 years, 200 years plus. There's huge literatures on both. It turns out that they're both right. That is, they both have their points, and in fact, there's good reason to perhaps try to combine them as Duncan Black proposed about 50 years ago. And with that observation, I will stop. Thank you.
Condorcet realize that Borda's method was the thing to do when he got a cycle? I mean,
no.
He must have thought about his cycles, right? Because
yes.
That's what was screwing up his voting method, and yet, because he had such blinders.
Well, Condorcet, it's funny how the interchange went. Condorcet knew that Condorcet cycles were a logical possibility. He pointed it out himself. He said that in practice he didn't think that they were very likely to occur. Condorcet, it was pointed out to Condorcet that his voting rule was highly manipulable. Borda. It was pointed out to Borda that rank order voting is highly manipulable. Borda said, "Oh, but I intend this voting rule to be used by gentlemen, members of the Academy of Sciences." So each of them refused to take the shortcomings seriously. If they had, perhaps they would have seen that there's a way of combining them.
So would your theorem hold if we changed Borda to give 1 point for the first person, 2 points for the second, and 4 points for the third?
It turns out that the actual Borda method, which has the equal spacing of points, dominates all of the others from this standpoint. That is, I'm including those voting rules in the set of all possible voting rules. Those are all dominated. So we don't want to have unequal spacing if we want to satisfy the four properties as often as possible. Yeah.
The cycle of length, like larger than 3, does it imply a cycle of length 3?
I'm sorry.
Suppose like we have this kind of we have cycles between like 5 people.
Yes.
Does it imply a smaller cycle or not necessarily? So
A cycle.
Yeah. Can you do like if you have a cycle among 5 people, like X big, Y is big, and all the way to like 5 people, or something a lot longer than 3 people? Can we necessarily reduce it to 3 people? Can we find a set of 3 people that has cycle, or not necessarily?
Not necessarily, no.
So do you propose this as a new voting system that we should adopt? You just have people rank it?
I'm certainly in favor of using Condorcet for elections where there's a single winner. Whether or not we extend it using Black's proposal so that we use Borda when Condorcet winners don't exist, I feel less strongly about. but certainly I think this paper gives some weight to the black proposal, and if you know, if I were a dictator and could choose the voting method, I might very well choose this one.
But in particular, that means that we would change the presidential elections or whatever to rank people as opposed to just vote.
Yeah. Now I should say one objection that is sometimes made to ranking systems like rank order voting or majority rule or any system where you don't just vote for a single candidate is that it looks as though you are putting an additional burden on voters. And I started this talk by saying that one of the things that we would like to do is to make things easier for voters, not harder. And doesn't producing rankings make things harder? But the point is that when you actually run an election, what you tell voters is that they have the option, if they would like, of ranking candidates. And they don't even have to rank them all. They can rank as many as they like. If there are 9 candidates running, as there sometimes are in European elections, they can rank 3 of them if they like. And then, in effect, the others will be tied at the bottom of their ranking. The ones who are unranked will be treated at the bottom.
But that won't break the Condorcet. I mean, if you have an incomplete ranking, that won't break the
No, it'll be complete. It just won't all be expressed. It won't be. No, but that's okay. It doesn't have to be strict. The majority rule is still well defined, even if some of the preferences aren't strict. It's messier, but it still works. But the point is that it's up to the voter to decide how many candidates to rank. Now, to come back to Florida in 2000, the quandary that what happened in Florida was certainly not unanticipated. A lot of people knew that this was exactly what happened could happen, and a lot of people who were thinking of voting for Nader worried about that because in effect, a vote for Nader was a vote for Bush. Well, that's precisely the case. We're giving people the opportunity to rank would have solved the problem. People who really like Nader could have put Nader first, but Gore second, and that would have. In that way, they could make the symbolic statement: yes, I really like Nader, and in an ideal world, Nader would get elected. But I know that this is not an ideal world, and he's not going to get elected. So I want to make sure that Gore still beats out Bush. That's the advantage of a system where voters can express more than just their top-ranked candidate. They have the opportunity, although not the obligation, to rank other candidates as well.
Silvio is telling me to tell Daron to ask his question, make his comment. I've never had to ask Daron to talk before, but come on.
I was just responding to, commenting to Silvio that we are still using Bayesian Nash here because the equilibrium concept is still Bayesian Nash. You need to actually form conjectures that other people are going to act on optimally, because otherwise, which domain is. So that was kind of a response to the this is not dominance solvable in the sense.
That's right. That's right. In order to know how to vote, since none of these methods are always non-manipulable, there's no voting method. It's always non-manipulable. In effect, you have to at least take into account the possibility that your vote that the outcome might be improved by distorting, and that gives rise to a Bayesian-Nash equilibrium concept.
Bayesian analysis to know that you should not change your voting? I mean, that seems like
no. If it were non-manipulable, you would not need Bayesian analysis because you could show that for every profile there would be no profitable deviation. But if the voting rule is sometimes manipulable, then to figure out how you should manipulate, you need to use Bayesian analysis. There's no dominant strategy analysis that's possible, or dominant solvable analysis.
Early in your talk, you said that it's not possible for voters to express the intensity of their feelings about different candidates.
Right.
But yet there are voting systems where, for example, you can assign a value from 0 to 100
Yeah.
to each candidate.
That's right. That's right.
And that, I'm sure, introduces other problems.
Yes.
Allow expression of intensity.
Yes, but the major problem that those voting rules introduce, at least in the language of this talk, is that they are extremely manipulable. I was talking about manipulation when there are 3 or more candidates, but if we're talking about a voting rule where you can assign points between 0 and 100, those are going to be manipulable even if there are just 2 candidates. Because suppose, for example, that I like candidate X slightly more than candidate Y. Y was almost as good as X. Well, I still like X more than Y, even though it's not by much. I am not going to be wishy-washy when I assign points. I'm going to assign all my points to X because that way I'm maximizing the chance of getting X rather than Y. We're not going to get any bona fide expression of intensity in this system if people are at all strategic-minded.
It's manipulable in the sense that people would not be expressing how they really feel.
They're true intensities. That's right.
It's not manipulable in the sense that people could do anything to that if their desire is to vote for X, then they're still voting for X, even though they've accentuated it more.
Well, but that's true. Okay.